Okay, so as was said by Mark, I would like to talk about this transition between microscopic dynamics. So just imagine that you have a gas, say in this room, and this gas consists of very small elementary particles, and so this is, say, the atomistic level description. And of course, it's a very complicated system because the number of particles is so large that you cannot say anything about, say, the qualitative behavior of this gas if you try to follow each individual particle. Okay, so that's really say our major problem here is to understand how you can have a statistical description of gases. Okay, so that's not one work, but a series of work with Thierry Bodino, Isabelle Gallagher, and Sergio Simonella, and it's still ongoing work because there are so many questions and very challenging problems. So I think there are room for many other people to think about all these problems. Okay, so here I will just look at a very simple system. So at the microscopic level, it consists just of small art spheres. Okay, so meaning that the motion of this Hamiltonian system is just given by rectilinear uniform motion of all particles up to collisions. Okay, and so when two particles touch each other, they will be reflected, and here the law for the reflection is just a specular reflection, meaning that you impose that, of course, the number of particles is constant. Two particles they will not they will stay two particles, and say their global momentum is preserved and their total energy is preserved as well. Okay, so if you impose all these conditions for spherical particles plus the condition that they cannot overlap, then you have a unique reflection law. Okay, and this is what is given here. So the new velocities after the collision will be given by this scattering law. Okay, and omega here is the vector, the normal vector to the spheres at the collision point. Okay, so now you see that it's a very simple system. It's an Hamiltonian system because say the total energy of the system, which is just the sum of the square of the velocity divided by 2 and multiplied by the mass, but here everything will be taken to be 1. Okay, the mass of the particles. Okay, so this energy is preserved. Okay, and you can see that it's, say, the equations are really simple. This is dxi over dt equal to vi, which is just a definition of the velocity of particle I, and dvi over dt is equal to 0 plus boundary conditions when two particles touch the boundary of this phase space. Okay, so this is the set of position and velocity of all particles with the condition that particles should not overlap. Okay, so this is really the simplest possible system at the microscopic level. And now what we would like to understand, of course, if the number of particles is large, it's very complicated to say anything about this. You see that this system is expected to be very unstable, because if you change just a bit the position of just one particle, you see that the whole dynamics will be completely changed. Okay, so this system as a deterministic system is really unstable, and so it's really important to have this statistical description. Okay, so you see that statistical here doesn't mean that you have noise in the dynamics, but that you just have a kind of uncertainty on the initial data. Okay, so the whole dynamics is deterministic, and the only unknown, so somehow, is the only randomness come from the initial data. So there are different settings to study this statistical problem. So maybe the most classical one is the canonical setting, meaning that you fix the number of particles. So this number, of course, will be very large, and we will say as a mathematician, we will let this number goes to infinity, but still it's fixed. Okay, and then you look at the probability density of the particles. So Wn here is a function of time and of all position and all velocities of all particles. So you see that this this distribution lives on a very, very big phase space, okay, of dimension 2d, d where d is the dimension of your real space, and times n, which is the number of particles. Okay, so you have just this very simple transport equation, which is called the Liouville equation, which just tells you that the position here, xi, will be transported by the velocity vi, okay, and then you have this equation is set on this phase space with exclusion, and then you have to prescribe the boundary condition, which is this elastic reflection. Okay, and then you have another level of randomness, which is referred to as the grand canonical setting, where you have both the randomness on the position and velocities of the particles, but also some randomness on the number of particles itself. Okay, so here you assume that this number of particles is distributed according to a Poisson process, okay, with the parameter mu epsilon, and I will discuss these parameters later on. Okay, so this just tells you that this distribution of n, okay, is mu epsilon to the n divided by factorial n, and of course then you have this partition function to normalize the distribution to be of total mass 1. Okay, so here you see that this initial data is just a product of f naught, meaning that, so if you just have this product here, this exactly means that all the particles are independent of each other and they are identically distributed. So IID variables are really the standard setting in probability. Then, of course, it's not true that they can be completely independent because of this non-overlapping condition. So you have to multiply by this indicator function of this phase space, okay? And then you have this probability measure on the number of particles. Okay, so that's our probabilistic setting. So you see that this randomness, so the statistics is not only about this initial distribution, and then once you have fixed your initial distribution, then you have completely deterministic dynamics. Okay, so that's the probabilistic setting, and now of course what we are interested in is this asymptotic limit when the number of particles is really big, okay, or the typical number of particles in the grand canonical setting is really large. Of course, it's not really interesting to have a statistical description if you have only 2 or 3 particles. Okay, so that's another topic, another mathematical field. Okay, so here we would like to have this number of particles, so either n in the canonical setting or mu epsilon in the grand canonical setting, to be very large. But of course, you see that if you fix the size of the particles and just let the number of particles be larger and larger, then after some time you have a packing problem. Just the problem of putting all the particles together, say, in a finite volume. And you see that, say, after a while, it's just impossible to put more and more particles. So here it's different. What we would like to have is what is called this Boltzmann-Grad scaling, and actually this scaling comes back to Maxwell. What you would like to have is kind of balance between 2 phenomena. So one is transport and the other is collisions. Okay, so you don't want to see a regime where all the particles are just stick together because you have a lot of particles, but a regime where you still have a kind of kinetic equation. So I will comment more about what is kinetic equation. But say what you should have in mind is that typically what you expect is that each particle will undergo 1 collision per unit of time. Okay, so that's what is called this Boltzmann-Grad regime, that each particle should have a finite number of collision, in average, of course, by unit of time. Okay, and so this tells you that you should have this relation between the number of particles. So here the typical number of particles is this mu epsilon, and epsilon here is the diameter of the spheres. And so what you require is that mu epsilon times epsilon to the power d minus 1 is of the order of 1. And this is simple computation that, say, if you just want to have, say, or the right order of magnitude, of course, this doesn't tell you that you will have exactly 1 collision per unit of time, but you see that you will have that 2 particles I and j will collide on this time interval 0t. So this is the same as saying that there exists a time s between 0 and t, such that say the initial position xi minus xj, so this is the initial relative position, minus s times vi minus vj. So say as long as you don't have any collision, the particles just have this uniform rectilinear motion. And so you would like this relative position to become less than epsilon for some intermediate time s. Okay, so you see that this exactly describes a cylinder. Okay, so meaning that, say, the position xj has to be in a cylinder with volume epsilon to d minus 1 times t. Okay, and then you see that as you can have collision with not only one particle, but with, say, essentially mu epsilon other particles, you see that the probability of will be of the order of 1, provided that this total volume here, so mu epsilon times the volume of each one of these cylinders, is of the order of 1. Okay, so that's really important that we are looking at this specific regime. And in particular, we cannot describe any gas with this, but only perfect gases. Because now if you look at the excluded volume, so the total volume occupied by the particles at, say, a given time, you see that each particle is of size epsilon to the power d, and now you have mu epsilon particles, and so you see that the total volume occupied by the particles is mu epsilon times epsilon d, and this will go to 0 as epsilon goes to 0. Okay, so this means that you can describe with this, so we'll see that Boltzmann equation is the right candidate to describe this dynamics, but you see that it cannot describe any gas, just perfect gases. And it's, of course, a very important restriction and something that say, in the future, we should understand. Now we can look at more dense gases.
So, okay, so perfect gases means also no viscosity, right?
Maybe I can just comment a bit on this. So this means that the gas can be viscous, but this implies, okay, that so viscosity will be a small correction, and you can see viscosity of the order of 1 if you look at incompressible regime. So for instance, the fluid equation that you can obtain from this Boltzmann equation and for these perfect gases are either the compressible Euler equation or the Navier-Stokes equation with a very small viscosity of the order of epsilon typically, or the Navier-Stokes, the incompressible Navier-Stokes equation. So, okay, if you just look at fluctuation and you have a small fluctuation for the velocity field, then you can rescale everything and have a viscosity of the order of 1. Okay, but this means that you cannot have, say, either you are compressible or you can be incompressible on viscous, but you cannot be compressible on viscous.
Okay, thanks.
Okay, so next, Okay, so now let me just explain the main question that we would like to study on this problem. So this is the global setting. Of course, you see that you can imagine a lot of different problems and more complex problems just by changing the microscopic interaction, especially if you have a very long range interaction, and the problem will be completely different. And you can imagine, so of course, to have many species and to have, say, other kind of interactions, such as electromagnetic interactions and so on. So of course, I don't say that this problem is somehow is a complete answer to Hilbert's problem, but say, even in this simple setting, there are a lot of questions that you can be interested in. Okay, so these are a natural question from the point of view of probabilities, but you will see that there are still a lot of work to be done. Okay, so first question would be, is it possible to have a law of large numbers for this problem? Okay, so you see that maybe I should first say that this kind of problems has been very, say that there is a huge literature on this kind of problems if you are at equilibrium. Okay, so without the problem of time. So here what is specific to our setting is that we really want to understand the dynamics. Okay, so it's really a dynamical problem. And so what we would like to do is really to mix the problem of the dynamics and the problem of the probabilistic problem. Okay, so that's already a first thing which is a bit different from, say, more classical problems in statistical physics. Okay, so here the problem of law of number would be to describe or to characterize the almost sure dynamics when mu epsilon tends to infinity with the scaling condition that mu epsilon times epsilon to the d minus 1 is equal to 1. Okay, so here we will see that this question has been answered quite a long time ago by Lanford, okay, but still there are some restrictions, and I will try to comment a bit on this restriction. And here we will see this Boltzmann equation, and I will try to explain a bit, okay. So then you see that, say, the law of large numbers is in probabilities is certainly the first question, but then there are a lot of questions, say, to look at the fluctuation around this almost sure dynamics, okay? So the first one, actually there is no numbering of this question, but say a very natural one is to characterize the fluctuation of the system. So first of all, the order of magnitude of this fluctuation, and we'll see here that it's, say, what you expect, so square root of mu epsilon, so 1 over square root of mu epsilon, the typical deviation from this almost sure dynamics. And then we will be able to characterize completely the dynamical equation for this fluctuation. Okay, so that's the first thing that you would like to say about this system. And then the other thing is, and it's really important if you have in mind rare events, and it's important especially for the study of climate and a lot of things like this, which is the question of, is it possible to see something else? Okay, so a completely different dynamics. What is the probability of observing another dynamics? And this is the problem of large deviations. Okay, so there are this. You see that these three questions are very natural in the context of probabilities, and they are very classical in statistical physics as well. But you see that say in most cases they are answered in the equilibrium case and not in the dynamical case. Okay, so really the challenge here is to understand how you can somehow use the classical tools from combinatorics and from statistical physics at equilibrium to study this dynamical problem. Okay, so let me maybe start by studying this result, which actually was the only result known for quite a long time. So I think the Lanford theorem is going back to probably something like 1973 or 1970, yeah, I think something like 73. Okay, and so this will give you a partial answer to question 1, so on this law of large numbers. Okay, so you look at this Boltzmann grad limit, so when mu epsilon tends to infinity with the Boltzmann grad scaling, and you look at this empirical measure. So the empirical measure is just so imagine that you are in the canonical setting. In the canonical setting, this is very simple. The empirical measure is just 1 over n times the sum of the direct mass at zi. Okay, so this means that you just average over all labels of particles. You will really use the fact that all particles have exactly the same mass, the same diameter, so they are what is called exchangeable. So you have a perfect symmetry between all these particles, and then you average over all the labels of all particles. So this gives you this empirical measure 1 over n times the sum of from I equal 1 to n of the direct mass at zi. So zi is just the pair xi vi. Okay, and so now in the grand canonical setting, you see that the number of particles is not fixed, and so the normalization of this measure will be 1 over mu epsilon and not 1 over n. Okay, so, and you see that here it's defined, this empirical measure is defined by duality. You see that it will act on what is called an observable, so h is quantity that you would like to observe, so it can be I don't know, the bulk velocity, or it can be so anything that you can imagine. So an average quantity over all particles, and you see that when you look at this empirical measure tested on this function h, it's just the expectation under the initial measure of 1 over mu epsilon times the sum from I equal 1 to n of this h of zi. Okay, so this is the quantity that you expect so to have a limit when mu epsilon goes to 0, you see that this doesn't make sense to have a limiting probability measure, because the probability measure lives on a phase space which is bigger and bigger, so you cannot really have a limit for this, but you will have a limit for this empirical measure. And this limit actually is the solution of the Boltzmann equation, which is written here. So I will not spend too much time on this equation because it's really a kind of monster from the mathematical point of view. I would just like to comment a bit to explain say the meaning of the different terms here. So you see that you have two. So in the right-hand side, in the left-hand side here, you have just transport. So if you forget about this right-hand side here, you see that you just have that this f, so this limiting empirical measure will satisfy the transport dtf plus v grad xf, meaning that you just have that particles are transported with their own velocity. Okay, so that's really very natural. And now you have this second phenomenon here, which is due to collisions. Okay, and so it tells you that, say, the number of particles with velocity v can be increased just by creating a new particle of velocity by collision between two particles of velocity v prime and v prime star, okay, which are somehow compatible with this v. Okay, so imagine that v is on the sphere with diameter v prime and v prime star. Okay, and this sphere is parameterized by a parameter omega here. Then you can create a new particle of velocity v by collision between these two particles here. Okay, and in a similar way, you can lose a particle of velocity v just by collision with another particle of velocity v star. Okay, and then you will have, say, of course, the number of particles will be always the same, but you will just have a jump process in the phase space. Okay, so particles, essentially, they are just moving in x. Okay, and in velocity, they can jump in the phase space just by collision with other particles. Okay. And you see that the specificity here of the Boltzmann equation compared to the microscopic dynamics is that somehow, if you can write this equation on the probability measure, you see that, say, the assumption, the underlying assumption is that you have, say, the probability of having a collision between here a particle of velocity v prime and a particle of velocity v prime star can be written as the product of f of v prime star, meaning that you can somehow you keep some independence between particles. Okay, so that's really what is called the Boltzmann chaos assumption, is that, say, you expect in this regime, which is the regime of a rarefied gas, that particles keep somehow their independence, and you can still write the joint probability of finding two particles at the product of probabilities. Okay, so that's really the main assumption in Boltzmann work, but here it's not an assumption, it's a theorem, so you can prove that you will somehow propagate chaos in this regime. Okay, because of course at time 0 you see that you assume that you have almost this independence, because I just assume that the probability measure was a product up to this small correction due to the non-overlapping condition. But then what we prove somehow in this limit is that this independence, this chaos, is propagated. Okay, and this limiting process is proved to be rigorous on a time interval 0t, and t is actually a very small time, and I will comment this a bit more later on. And this small time t depends only on the initial data f naught. Okay, so that's say a very actually it's not a very complicated statement. You say that you start from the empirical measure and then you can pass to the limit almost surely somehow. It tells you that it will be a solution in the limit of this Boltzmann equation, and with this bad restriction that it's only true on a very small time interval. Okay, so that's what I call here problem number 2, and then maybe I will start with this problem number 2. You see that this short time is actually a fraction of the average time on which particles have one collision. Okay, so that's somehow it's not very good, it's even very bad, because you see that you can prove that you will converge to a collision model, but where you have almost no collision. So it's not true that you have no collision, because you have something like mu epsilon divided by 5 or divided by 2. I don't remember exactly. You can keep track. You can try to track all the constants and see what is this fraction of the mean free time. But okay, it's not really interesting. The point is that essentially you will see very few collisions. Okay, and so there are many questions about this. Of course, so one of the specificity of the Boltzmann equation is that you expect some relaxation towards equilibrium because of this collision process. And so it's very bad news that you cannot see really this relaxation, because you can justify the Boltzmann equation just on a very short time. And so there is a natural question to understand where this limitation comes from. Okay, so is it just a problem, or is it a more, say, complicated problem due to the structure of the Boltzmann equation? Maybe I should tell you that the Boltzmann equation is really a complicated equation. So just to have solution, it's complicated. So say the only notion of solution for which you can really prove global existence under, say, simple physical assumption is the notion of renormalized solution, which is also related to this problem of say that something not really good happens after a short time. Okay, and then there is a question whether it's possible or not to have a counterpart of this theory of renormalized solution at the level of microscopic dynamics. Okay, this is something that I will not really talk about today, but this is really something that it is really part of our next, say, our research program for the future. Okay, so what I would like to comment a bit more today is this problem number 1, and it's something that has been mentioned in the introduction by Marc. So you see that you start from a microscopic dynamics, which is an Hamiltonian dynamics, so everything is reversible. Okay, you can just imagine that you have a billiard, you play the billiard for a time t, then after a time t you decide to revert all velocities, then you know that, say, at least in principle, maybe not in reality, but at least in principle, if you revert all velocities, then you will be back to the initial state up to the sign of the velocities after exactly the same time. Okay, so at the level of the microscopic dynamics, everything is reversible, and you have this say, you have also Poincaré recurrence and so on. So it's really a very nice Hamiltonian system, even though you have this kind of singular interaction. Okay. Now, if you look at the limit equation, so this Boltzmann equation, it's completely different. Okay, maybe it's related to the fact that this equation is so important that somehow it encodes the second principle of thermodynamics, which tells you that the dynamics is not reversible. You have a Lyapunov functional, which is the entropy, which is called the entropy. Okay, which so for physicists, entropy is increasing. For mathematicians, because of different convention on the sign, the entropy is decreasing. But anyway, it's a monotone function. So Lyapunov functional for the evolution. And so you see that if you start from given a configuration at time 0, you let the system evolve during a time t, then at time t you revert all velocities, and then you still let evolve the system for the same time interval, you will never go back to the initial state. Okay, never. Except if you start from an equilibrium system, and then everything is at equilibrium forever. Okay, so you see that somehow it's really different. Say the microscopic dynamics is deterministic and the Boltzmann equation is not. Okay, and so this is actually a philosophical question that occupied a lot of people, including physicists and philosophers and also mathematicians. And it was one of the reasons why the Boltzmann equation, at the time of Boltzmann, was not really recognized as possible model for this system of particles. Okay, so it's really an important question, and maybe what I would like you to understand is that somehow this is kind of pioneer work in the sense that it's a bit in advance on quantum mechanics, meaning that you see that you have two levels of things. So you have the dynamics, which is reversible, and it will be reversible forever. And then another point of view, which is the point of view of the observer, okay? And the Boltzmann equation is really at the level of this observation. And you say that, say, the information that you keep on the system is not the whole thing, okay? So somehow you lose some information on the system, and the fact that the Boltzmann equation is not reversible is just due to the observation and the fact that you record only part of the information on the dynamics. I think it's really important to have this in mind, as there are many crazy explanations about this, the irreversibility in the Boltzmann equation, about the sense of time and the arrow of time, and this is really crazy. So here, that I think that's maybe, if there is just one thing that you should remember from this talk, is that it's really something which is really important, that the Boltzmann equation is a statistical description, meaning that you lose some information, and that's exactly the reason why you have irreversibility in the Boltzmann equation, even though the underlying dynamics is reversible. Okay, and what I would like to explain in the rest of this lecture is that maybe you can keep actually more information with a more complex mathematical say framework, and then you see that that's really the point is not the problem that the dynamics itself is, say, irreversible, but really a problem of keeping the information in the limit. Okay, so that's what kind of an introduction about the problem, and now I would like to give you, of course, not all the proof of all theorems and not very detailed things about all the answer to this different question and problems that I mentioned, but say at least give you an idea of the tools that can be used in all this this work, and how they can be connected to different parts of mathematics. Okay, I think it was something that was really well said in the introduction. I find that this domain is really fascinating because you have links with probabilities, PDEs, combinatorics, and many different topics in mathematics. So I would like to just give you a flavor of this. Okay, so maybe I should first say a couple of words about Landforth's proof, because it was really our starting point. So right now we have, say, other ways of looking at this problem, but it's really a more recent work, and I will not comment on this. But okay, I think it's good to start with a couple of words about this global strategy that has been proposed by Landforth. So the idea is that, okay, you have this very complicated probability measure, okay, which is given by this initial data, and then what you would like to understand is how this probability measure is transported by the dynamics. Okay, so of course everything is very well defined. You have this probability measure, you know how to transport it, and then okay, you can write another probability measure at any time, but of course it's a very complicated object, and you are not really interested in this complex object. Okay, so what you are interested in is our kind of projection of this probability measure on finite dimensional subspaces. Okay, so that's what is called a marginal or correlation function. So here these are this capital F epsilon n. So you see that once again you test this F epsilon n on some observable. Now the observable is a function of a small n variable. Okay, so small n can be anything between 1 and plus infinity. Okay, and so you test so this correlation function is defined as the probability measure on a finite dimensional space. such that it gives you the expectation of, you see that now it's not the empirical measure, but kind of generalization of this empirical measure, because now instead of looking just at Hn of just one configuration of one particle, you look at the configuration of small n particles, and you look at all possible n-tuples of particles. Okay, so that's the definition of this correlation function. And now if you write the Liouville equation for all W capital N, and you average over with the ground canonical setting, then you can see that it's just a computation, okay, where you use essentially Green's formula. You see that this correlation function satisfy an equation which has the same structure as the Boltzmann equation, where you have transport here in the left-hand side. Of course, now you have the transport of the small n particles. And in the right-hand side, you describe all possible collision between particles I, where I is between 1 and n, and another particle that I call n plus 1. Okay, and this just comes from the fact that you have this Green formula, and the fact that your phase space is defined with this non-overlapping condition. You see that when one of the particle I touch another particle, then you have a boundary term. Okay, so that's the general structure that you have, and this is what is called the BBGKY hierarchy. Okay, and then you see that if you would like, so now f epsilon n is a function, a probability measure, which lives in a given phase space. And so here you could say that now you can take limits in this when epsilon goes to 0. But now you see that you are a little bit annoying, because you see that, of course, on this Fn, you don't obtain a closed equation. The Fn will depend on Fn plus 1, and then the Fn plus 1 will depend on Fn plus 2, and then you end up with a whole hierarchy of equations, and so it's not very satisfactory, because you cannot say anything on F1, which is, say, the limit of the empirical measure is just F1. Okay, so you would like to work on this hierarchy to be able to take a limit and then prove that you get the Boltzmann equation. And so what is really important in this Lanford strategy is that you transform this. So here you see that you have PDE, so transport equation, and now you write a formal solution of this in the form of a series expansion of operators acting on the initial data. Okay, so you will write that Fn of t is a sum of operators, and I will try to explain what these operators are, acting on the initial data. Okay, so on the initial data, of course, say everything is well defined, just because this is the initial data is given. Okay, so now what is this operator Qn plus m? You see that somehow what you would like to do is to track back the history of one particle or n particles, if n is not 1, and to back to time 0. Okay, so that's something that you can illustrate like this. Okay, so imagine that n is equal to 1, so you start with one particle, and what you would like to do is to say, okay, what can I say? Can I compute the probability of finding this particle at a given position with a given velocity, just tracking back his history up to time 0. So you see that you say, okay, this particle, for some time, it will just be transported, okay, without any collision. Then at some time t1, and this t1, of course, will be somehow not random, but it's a parameter that can take a lot of different values. It will undergo one collision here with another particle. And so if I would like to know the history of this particle 1, then I need to follow the history of these two particles, okay? Then I go back until one of these particles have another collision, okay? And so, and I do so until I reach time 0. And at time 0, of course, I know the probability of this configuration, okay? So that's exactly, so this representation with the series expansion is exactly this thing that you follow somehow all possible trajectories. Of course, that these are not exactly trajectories, because I do not keep the information on all particles, but just on the particles that somehow are involved in the story of this tagged particle. here. Okay, so that's exactly what we do. So here you see that you have this f epsilon n. So here is the picture corresponding to n is equal to 1. Will be the sum on all possible number of collision. You say that, okay, the number of collision is something between 0 and of course, at most you have an infinite number of collision between time t and time 0. Then you see that you can represent the history by a collision tree. Okay, so this capital A and M is the set of trees with n roots, okay, and m branchings, okay. So now you have this A and M, and then you integrate over all parameters of the collision. So you see that one collision here will be parameterized by, of course, the time where it happens, but also the velocity of the new particles, which is created here, and also the impact parameter between the two particles. Okay, so that's time of collision, velocity of the new particle, and impact parameter here. Then you have here something which is a cross-section that I will not really detail here. It's not, okay, it's a big technical problem, but I think it's not really important to just understand the strategy. Okay, so it depends on all intermediate velocities and so on. And then, of course, you are back to the initial data. And so you just take the probability of the configuration that you obtain by this construction here. Okay, so you see that once you have all these parameters, both the number of the collision trees, and all these collision parameters, then you can construct a pseudo trajectory, because you see it's not trajectory. You keep only some very partial information about not all particles, but only a couple of particles, and you see that even the number of particles is not conserved between here and here. Okay. And so you see that you have essentially backward transport here, and then you add a new particle each time you have a branching. Okay, and then you have two possibilities at each branching point here. Either you have a scattering corresponding to the gain term in the Boltzmann equation, or you have no scattering and it's the loss term. Okay, it's also okay. So anyway, you have a representation with a series expansion and something very geometric object of this very geometric representation of all these elementary terms in the series expansion. Okay, so that's really I think it's really important to have an intuition on this thing, and it will be really important in the sequel. Okay, so now you see that you can understand it's not really complicated to understand Lanford proof once you have this geometric representation. You see that essentially there are two steps in the proof. So one is to prove that the series expansion is converging, okay, and uniformly converging. But here you see that essentially you can just look at this. You see that you have a sum over m. Here you have the number of trees with m branching, okay, starting from n roots. And then here you have, so I will just discard integration with respect to v and omega. It's not really important. It's a bit technical, but not really important. And then you have this integration over a simplex in time. Okay, so if you look at this, you see that the number of trees is given by this n plus 1 and plus m minus 1. Okay, and then if you integrate over the simplex in time, you get t to the m divided by factorial m. And so each elementary terms is estimated by something like this. So this is a combinatorial factor that, so it's less than 2 to the n plus m. Okay, and then you see that if time is less than 1 over c0, you see that the series will be convergent. And that's exactly why you have this restriction in Lanford's theorem that you need this series to be convergent. And okay, it's both a technical problem and also a bit problem related to the fact that the Boltzmann equation is not very well defined after this time. Okay, so that's the first point. So just having a uniform bound on the series expansion, and then you have to look at the convergence of each elementary term. Okay, and then you see that. So what is the difference between say what is the limit of each elementary term? So you see that when the size of the particles tends to 0, you expect two different things to happen. So first of all, when you add the particles, instead of adding it at a distance epsilon from its parent, you will add it exactly at the same position. So you don't have any spatial shift where you add the particles. And say the most important difference is that once you have two particles here in the bath, okay, or in your dynamics, they will never see each other, okay, because their size is 0, so they will just cross each other. While when epsilon is fixed, given non-negative, you see that the two particles is at some point they are at the distance epsilon, they will have a recollision and they will have a completely different dynamics. Okay, so the main difference when epsilon is 0 or not 0 is the problem that you can have these recollisions. Okay, so when epsilon is not 0, you see that these particles 3 and 2 will be deflected by this recollision, while in the limiting dynamics they will just go straight. Okay, so then you see that, that there is no way that these two trajectories are close to each other. So the thing that you have to prove is that these recollisions happen only for a very small set of collision parameters. Okay, so it's three. So you have two different cases. So either you have a good set of collision parameters, and then the two trajectories can be coupled; they are really close to each other, or you are in the bad set of parameters. But this bad set, you integrate over this bad set is small, and so the contribution of this bad set will be very small. Okay, so that's just idea of flat force proof. Okay, so now what I would like to do is, I don't have so much time, but I would like to explain a bit how we can go further. Okay, so one of the problems that I would like to answer is the problem of this reversibility. Is it possible to keep more information on the system in order to keep something which is reversible? Okay, so to keep enough information in the limits to keep something which will be still reversible. So this is the first question. And then there are the two other questions about fluctuations, so central limit theorem and large deviation. And so all these questions actually can be answered by, so still on this short time, by looking at something which is very, looking at exponential moments. Okay, so instead of, so if you remember this correlation function, they give you something about, say, polynomial moments, so the expectation of hn with n, or the expectation of the empirical measure. Okay, now you see that instead of looking at the expectation of the empirical measure, I will look at the expectation of the exponential of the time of mu epsilon times the empirical measure. So you see that this actually encodes much more information on the system. Okay, and this is related to what is called in statistical physics cumulance. Okay, this say at least for small time or small h, you can expand this function because it's analytic, and then the different coefficients that are involved in this expansion are what are called cumulants. Okay, so that's a very classical definition in statistical physics, and I will not really comment on this expansion here. Okay, but what you should remember from this is that if you look at the correlation function, somehow the first correlation function encodes, say, this law of large numbers. But then if you look at the second order cumulant, so the second order correlation function, you see that you will have two parts in this second order correlation function. One which is almost the factorization of the first one. Okay, so which would be exactly equal if you have an exact propagation of chaos, okay, plus a small correction. And this second order cumulant will be exactly this small correction. Okay, so the advantage in looking at this cumulants compared to a correlation function is that somehow the information is not repeated. Okay, so if you look at the correlation function, the second correlation function encodes, say, the leading part of the second correlation function instead of the first correlation function, which is standardized, and then there is a small remainder. But now, if you look at the cumulants, then the second order cumulants just encode the information which is not already encoded in the first order correlation function. Okay, so that's much better because somehow you will really focus each time on the information which is missing in the previous coefficient. Okay, so now you can have, say, in a similar way, we add a geometric representation of correlation function, but now you can also have a geometric representation of this cumulants. Okay, so you start from the same representation with collision trees and so on. Okay, so here I start from 5 collision trees. Okay, and then I try to see what is the obstacle to have a factorization to prove that this is exactly the factorization of 5 times, okay, the first correlation function. Okay, and you see that the first reason why you cannot factorize is that maybe at some point you will have a recollision between these 2 trees here. And then you see that you cannot write that's not a product of this times this, because here you have, say, somehow 2 particles will recollide, and so then they will be dependent of each other. So the 2 trees here will be connected forever. Okay, so the first thing that you do is that you group. So you introduce a partition of your different collision trees here in forest, and forest are all the trees which are connected by a recollision. Okay, so as soon as you have a recollision, of course, you see that the probability of having a recollision is something which is very small. So you expect that's say somehow the probability of having a forest which is non-trivial is small, but still it will be important because it will be really the most important thing to understand these cumulants. So now you have these forests. Okay, so now by definition, 2 forests are, say, decoupled in the sense that they do not have any collision between themselves. Okay, so you can write the trajectory here and the trajectory here in an independent way. But still, they are not independent just because you have this condition that they should not overlap. Okay, so you see that it's really, they are not connected, so they don't see each other, but still they are not independent because just the fact that they should not overlap is somehow a condition that breaks independence. So then you use something which is really, really classical in statistical physics, which is to expand this non-overlap condition with cumulants. Okay, so you say that so this is the condition that the forest should not overlap, and you say that you can expand this with correlation with cumulants. Okay, so just writing that that if you so just imagine that you have 3 forests, you will have that the first term will be 1. Okay, so they are independent, and then it will be minus the fact that 2 forests are just crossing each other, and then plus the fact that 3 forests are touching each other, and so on. Okay, so you just expand this non-overlapping condition, and then you group forests in jungles. Okay, so meaning that you write that having no overlap is 1 minus having an overlap, and each time you have an overlap, it's a different connection. And this corresponds to the, so the forests are these blue packets, now the jungle are these black packets here, and this forests here are just, so you see that the dynamics of the different forests are independent, but you have the condition that these 2 forests should overlap. Okay? And then there is a last source of correlation which comes from the initial data. Okay, so you see that now being in the cumulant of order n means that somehow, if you look at this, you are in a big packet here, a yellow packet here, which will be the whole thing. So meaning that all the particles or the trees are connected either by recollisions or by overlaps or by the initial data. Okay, so you see that, of course, said if you think about this correlation function, the leading order term will be the case where all trees are just independent of each other, and this corresponds to the factorization of F1. But then you see that you have correction which comes at any order due to the fact that you cannot have all these source of correlation, recollision, overlaps, and initial data. Okay, so you have a complicated formula which is here for the cumulant of order n. So you see that you rescale this, okay, this mu epsilon to the n minus 1. So we decide to introduce this renormalization because this will be the good renormalization to have say a cumulant which is of the order of 1. Okay, so it really tells you that you look at finer and finer scale in the system, because the mu epsilon, of course, is a very big parameter, and now you take it at the power n minus 1, which corresponds to the n minus 1 clustering constraints. Okay, and then you look at all possibilities of connecting your trees by either overlaps or initial data or recollision. Okay, so this gives you this complicated formula. Of course, I don't care about the formula, but what is important here is that you will have n-1 independent clustering constraints. So meaning that being in the same packet, in the same cluster, means that if you look at the L1 norm of this guy, it will exactly compensate for the mu epsilon to the n-1 here. And so in the end, you end up with the L1 norm of this cumulant, which is factorial n, which corresponds to all possible trees connecting all the, say, you have a trees over the set of trees, okay? So all possible graphs, minimally connected graphs connecting your trees 1 to m, okay? So this is the combinatorial factor. And then here, this is due to this clustering constraint. If you have this clustering during a time t, then it's proportional to t to the n-1. Okay, so you see that it's really much better than the first estimate that we have on correlation function, because we rescale this, so we really can look at all this small deviation with respect to the say chaotic situation where everything is factorized. Okay, so it's really much better because we can really look at this very fine structure. You see that the cumulant of order n is typically of the, if you do not rescale, it's typically of the size of mu epsilon to the minus n-1. Okay, so it's really something which is really, really small. Okay, so I think I have just a couple of minutes to end this talk. So what I would like to say that you have, so this was the counterpart of the first step in Lanford proof. So having this a priori bound on the series expansion, and then you have the similar second step where you just take limits as epsilon tends to 0. So you see that you will have exactly the same kind of asymptotic process where you add particles without shift, you have a free transport instead of transport with recollision. And then, of course, for the cumulant of order n, you have to keep track of some of the recollisions or some of the overlaps, exactly n-1 of them. Okay, so you see that, so the typical for the second order cumulants, so what you the typical thing that you will keep is this picture here without the non-clustering recollision. So you will keep exactly one recollision or exactly one overlap. Okay, so you know exactly the limiting structure of all these guys. Okay, so maybe I can just conclude by telling you two important consequences of this analysis of cumulants. So the first one is that you see that we looked at the exponential moment and this exponential moment, of course, is related to the characteristic function. Okay, so up to rescaling in mu epsilon. Okay, and so you can relate say the characteristic function of the fluctuation field, which is defined here as the difference, as the rescale difference between the empirical measure and the average here. Okay, so this is the fluctuation field, and you can prove that it will converge in law to the solution of this stochastic PDE. So here you see that you have two terms in the stochastic PDE, one term which is the linearized Boltzmann collision operator here, okay, so with transport and collision, and plus a noise. Okay, so you can prove that you can really characterize the noise. You can prove that in the limit you get a Gaussian process. So if you want to characterize the fluctuation, you get a Gaussian process and you get exactly this stochastic PDE for the evolution of this Gaussian process. Okay, so I will skip a comment about the proof, but say just keep in mind that it's really a consequence of the previous results just by looking at the characteristic function, which is related to the exponential moment. Okay. And the second theorem that I would like to mention, which is also a consequence of this exponential moment, is that you can also characterize the large deviation. Okay, so looking at the probability that, say, another trajectory, so that your empirical measure is another set of say somehow far from its average, which is the Boltzmann equation. So you if you have this, say you look at another set of trajectories, then you can characterize the probability of being in this other set of trajectories by a functional, which is the large deviation functional, which is completely explicit. Okay, so and this functional coincides with the functional which was predicted by both by physicists and also by Fredun, Rezak, and Liu for stochastic dynamics. So here you see that it's different. The dynamics itself is deterministic. Only the initial data is random, but then you obtain the very same thing, meaning that you see that propagation of chaos is a very, very strong property of this Boltzmann-Grad limit. Okay, so just one comment. So the way you characterize this this large deviation functional is by writing the equation for this exponential moment, so the cumulant generating function. And the very important thing is that you can prove that it will satisfy this Hamilton-Jacobi equation, which is a bit, say, similar to the Boltzmann equation, except that now this equation, of course, it's a very awful equation because it lives. So now H, you see that the capital I here is a functional which depends on the function H. So it's living in the very, very awful functional space. But now this equation is reversible. So meaning that if you keep not only the information on the first correlation function, but on all cumulants, then you end up with something which is in the limit is still reversible. So you have answered the three questions. The first one, central limit theorem. The second one, which is large deviation functional. And the third one, which is somehow, can you remove this loss, this loss of information, which is responsible for the irreversibility? And the answer is yes. If you keep the exponential moment, then you end up with something which is reversible. Okay, I'm sorry because I was a bit too long, but I thank you very much for your attention.